Bandwidth for changelog is provided by Fastly. Learn more at fastly.com. We move fast and fix things here at changelog because of Rollbar. Check them out at rollbar.com. And we're hosted on Linode Cloud servers. Head to linode.com/changelog. What's up, Gophers? It's not too late. If you're planning to attend KubeCon Cloud Native Con here in North America later this November, know that we have just entered late registration pricing, but you can still save 10% off your registration when you use our code KCNA-changelog19. Again, that's KCNA-changelog19. Check the show notes for links to learn more and register. Welcome to Go Time, a podcast featuring a diverse panel and special guests discussing cloud infrastructure, distributed systems, microservices, Kubernetes, Docker, and also Go. We record live every Tuesday at 3 p.m. Eastern, noon Pacific. Join the community that's live with us in real time during the show in the Go Time FM channel in Gopher Slack. Follow us on Twitter, we're at GoTimeFM. Listen live at changelog.com/live or subscribe at changelog.com/GoTime. And now on to the show.
Hello, everybody. Welcome to Go Time. I'm here with Manish, Jain, or Jon?
Manish, Jain.
Jain, sorry. And then I'm also here with Karl McGuire. Karl, you want to say hi?
Hey, everyone.
And Johnny Borsico.
Hello there. Good to be back.
And I am John Calhoun. Today, we're going to be talking about caching. So we just want to talk a little bit about what it is to start, why it's useful, that sort of thing. And then Manish and Karl are both from Dgraph, and they recently released a caching library, I believe. Is it a library?
Yes.
Yes, it is a library.
Yes. So they released a caching library that we want to talk about a little bit, so you guys can learn a little bit about what they learned building it, why they built it, what problems it solves, that sort of thing. Okay, so to get started, do you guys want to tell us, or anybody, I guess, talk about what caching is and, why it's useful?
So computer systems these days are limited by the speed of the internal components, and the fastest component that any computer system has tends to be the RAM, right? After that, the faster one would be lower than RAM would be SSDs, and then comes hard disks. And systems in general have a problem of trying to store the data in a cheap possible way, while also trying to make the request as fast as possible. So you are doing this juggling between keeping data in a RAM, which is more expensive, quite limited, versus keeping data on disk, which is cheaper and you can fit a lot of data in there. So the job of a good cache is to try to keep the data in RAM so that any future requests can be served faster than having to read it back again from any disk. And so caches are typically judged by, the terms used are hit ratios or miss ratios. And a typical hit to miss ratio would show how effective a cache was in serving the request from the RAM instead of going back to the disk. Or any other system outside.
So one of the things that I think it's worth also level setting here is that we're talking about a caching sort of library, not a caching server, right? So a lot of developers are typically in the mindset of thinking that, well, maybe I'll use Redis or something, which is a popular caching server, or maybe I'll use some other thing, along those lines. But what we're talking about here is not something that's going to go over the network. This is something that's on host, correct?
That is correct. The idea of Ristretto was to be used within our other systems, like Badger, which is the embedded key value database, and more importantly in Dgraph, which is a server which you kind of like go over the network with. But again, we want to make sure that we are being effective in our request resolution. Now, as you mentioned, there is Redis, there is Memcached, which are essentially caches but over a network interface, so you can dedicate an entire system just for the cache itself. And funny enough, Google's web search index, the top tier of the index, is running in this thing called Mustang, which is completely in RAM as well. So I would say a good cache like Ristretto could be made to work as a network system. but that's not what it does out of the box.
We talk about like, using an in-memory cache. It's not necessarily new, but I feel like more recently people are starting to use them for much, much larger data sets. Do you think that just has to do with the fact that RAM is getting cheaper and it's possible to stick much larger data sets into a cache? Or are there other reasons for that?
I would say RAM is definitely has gotten a lot cheaper than before. At the same time, I feel people are just more willing to dump the data into cache these days because of how, do I want to say advanced these systems have become. Redis can do quite a lot of things. It can literally become your data structure. It can add to lists. It can do maps and sets. And not that I have personally used Redis at all, but I think a lot of it probably also comes from how effectively Facebook used memcached and used it in front of all of their SQL queries. So I think just by how willing the big companies have been and how generous they have been in using their caches, people are more willing to use the cache as well.
You talked about having the cache in front of like a SQL database. In this day and age where a lot of people talk about like NoSQL and things like that scale more, is that as much of a concern now that you can realistically use a cache of some sort rather than jumping straight to like a NoSQL database? I guess what I'm saying is the database decision, like trying to get something that's highly scalable, as important now that you probably could realistically get pretty large just using a SQL database and throwing caches in front of that?
Caching would only take you so far. The actually any good multiple version concurrency control system, it becomes very hard to use cache in systems like those, which includes Dgraph, because every transaction could return slightly different results based upon what happened just before. So I would say at least Dgraph, and I think any good database would try to avoid doing a query level caching. They would only do some data level caching, and even then would have to be sophisticated about it. Now, I think the argument about, hey, why don't I just use a cache in front of SQL instead of like having to use, let's say, NoSQL or having to use a graph system, they provide different things. The functionality of a graph database, for example, can be quite, I would say, evolved. And I'm obviously biased. I don't want to upset any SQL people, but it just gives you a lot more functionality, and it's hard to achieve that. Like caching would not get you there. On top of that, caching across multiple systems is also a hard thing because of just the race conditions involved, and so on and so forth. So memcached, for example, gives you a cache compare and set counter, so you know that if two different systems are trying to update the same key, one of them would fail. That almost becomes like a transaction, but at a lot more atomic level, at a key level. So then if you're putting a cache across systems, you have to deal with those kind of issues. And the more you deal with these things, the more complex your code becomes, and so on and so forth. So I think caching helps, but it is not replacement for the different functionality offered by different databases and the scale of these databases, and so on and so forth.
Say I need to interact with say I have an application that's basically, say it's a service, right? And it's using, on my host, it's using the caching library to cache something. So if I have multiple services that each have their own cache, like is it possible that I'm depending on how you use it, I would imagine, but is it possible that if I hit one service, it's going to have data that another service might not have, right? But because you can't control which host you're going to hit, therefore you can't control which data you're going to retrieve from which cache. So like if you need, is there rather, how do you ensure that the same data is on every node, right? When you're dealing with sort of like the cache on the host itself.
So I think a good cache plus database system, let's say running on a single server, should appear seamless to the caller. So even if they're calling multiple different servers for, let's say, multiple different sets of data, the cache should be smart enough to make sure that you are getting the latest version of the data without the systems having to know about the cache, right? So the systems themselves should be completely unaware that the other system might be using a cache. I think that's how I think a good cache should work like. Now, obviously, If you're running like cache servers, which are running outside of these systems, things become a bit more complicated with the race conditions and so on and so forth. But if you're actually putting cache on the host itself, you, as an outside entity, outside client or another server, you would just make the calls as if there was no cache, and you should expect the same results.
Okay, so from an application developer sort of perspective, I should expect that it's quite possible that if a particular client happens to hit, a service that's on a host that hasn't perhaps cached a particular piece of data yet, that there's going to be a little bit of latency while the data is retrieved and put into memory and then returned, and then subsequent hits, right, from the client could hit a server that either already has or doesn't have the data, right? So that should be part of how I should think about this as a developer.
That's right. Yeah, I think, and sometimes if you play with let's say Postgres, and you will shoot a query to Postgres, you can see the first query tends to be relatively slow, but then the queries after that become extremely fast, and that is just the magic of the cache. So I think I've seen in certain systems people will build this cache warm up mechanism when they run their servers, so that it would pick up what they think would be a decent initial set of data, and then over time it would just improve to hopefully increase the hit ratios. Essentially, that's what any cache is going for, is to be utilized as frequently as possible.
To be clear, things like hit ratios and stuff like that only truly come into play when you don't have enough RAM to store everything, correct?
That is correct.
Okay. So like for anybody who's not familiar with caching, sometimes you can be lucky early on where you can query an API and get some sort of data or whatever it is that happens to be pretty static. And if you can store it all in memory, your cache implementation almost doesn't matter that much at that point, because it's literally just throw it in memory and keep it there. I've actually done this myself where, I'm hitting a couple things and like pulling the data, and then I'm basically rendering Markdown that's rendered into HTML from that point on. So I can just store the HTML and I never have to hit that API again. So the first query is kind of like Johnny was saying, it's slower, like hitting a SQL database, but after that point, it's very, very fast. So when Manish starts talking about, having hit rate, good hit ratios and stuff like that, what he's referring to is the fact that when you get to a point that not everything fits, you have to decide, what do I throw out and what do I keep? And that becomes a really complicated problem because you never truly know what people are going to need next.
Yeah, along those lines, I'm hoping you're going to get into sort of the cache invalidation strategies that you use as well, to do that sort of performant sort of a jettison that John's talking about. I think there could be there's some stories there you can probably tell with regards to sort of the latency that's involved in there.
John, I must say that I envy you when you say that your cache did not hit capacity and you could just store everything in there. That would be a great world to live in, where you can just put everything into RAM and never have to worry about it. All your queries are super fast, everybody's happy. But yes, unfortunately, that's not the case. Now, to give you an example, I think in Dgraph we deal with terabytes of data, and the RAMs, even the most generous RAMs would be, let's say, 64 gigabytes, and some of them I've heard about 128 gigabytes. That's the RAM available in the system. Now, that's actually pretty generous, right? I wouldn't expect every person to give us a system with 64 gigabytes of RAM. In any case, it is still limited, and that's when we run into the capacity of the cache, and that's when we have to figure out clever ways to determine what we keep and what we kick out. Predicting the future is extremely hard, but you basically just learn from the past and try to see what would be valuable, and that's what we have tried to do with Strato in our implementation.
Could we start with some history? Like, can we talk about, I guess, some of the like more basic caches that people have started trying and started out with to sort of figure this stuff out? Like, I think one that most people have probably heard of is just a least recently used cache, which is, a relatively simple idea of something in memory that, whatever object has been used least recently, that's what you evict whenever you need to replace it with something. I think that one's even common enough that I've seen it pop up in interview questions, which is slightly crazy, but it does pop up in interview questions. And I think Java even has a linked hash map in the standard library, which is essentially at least recently used cache. It might not be the most efficient one in the world, I'm not sure, but it essentially serves that purpose. So obviously that's a model people can use. Why does that not work at scale? Why is that something that, it's relatively simple to understand, I think, where you're just keeping track of what items were used most recently. But why does that not end up working at scale when you're getting in large data sets?
I think before we begin the discussion, I should probably kind of explain the scale in this case. By scale, at the internal system memory level, we're talking about scale in terms of the number of cores, the number of Go routines, the number of concurrent lookups that could be happening. As opposed to when we talk about database scales, we talk about different machines and how much terabytes of data you can keep, right? So now scale in this case is the number of concurrent accesses that could happen. And so we tried in Dgraph a bunch of different techniques, right? The simplest thing that anybody could do is take a map in Go, put a mutex lock around it, and then for every get you just do acquire the lock and you do the retrieval. Now that would work, and that works very nicely for some basic use cases with low concurrency, but it becomes a hard challenge on what to evict and when. If you do it badly, you would directly affect your hit ratios, which means that things would actually slow down. Because note that a cache can also slow things down, right? Cache is an extra step that you have to do. You not only you have to retrieve the data from the underlying hard disk or system, etc. You also have to first check in the cache if the data exists, and then later on put it into the cache. And that lock acquisition and release can become a source of contention, as we found in Dgraph. So in Dgraph, what we had done was we took the LRU implementation by Group Cache, written by Brad Fitzpatrick of Memcached fame and obviously the Go team. And it was obviously a very nice implementation of LRU cache that we picked up. We put a lock around it and we started using it. And we knew that we had to optimize it at some point, but we did not realize how bad it was. At some point, we was looking at a particular query. This is 1 year after implementing the system, and we realized that if we were to remove the cache, our queries would improve by 5 to 10 times. Even like a 30% query improvement is a good day for an engineer, but when you increase it 10 times, that's just incredible, right? So we immediately removed the cache and we started to look around to see what we could use. And that's when the whole idea for Ristretto started.
Obviously, you built this for your specific needs, but I'm assuming that you also sort of thought of this as like a more general purpose library as well. Like, how did you go about deciding, like, how are we going to test this? What metrics matter the most for us? Because I'm assuming it's like most software where there are some trade-offs. It's really hard to, like, have the best of everything. So, when you were trying to design that, was it just mostly focused on your specific needs of a lot of concurrency and a lot of, queries like that? Or did you just sit down and come up with a generic set of requirements?
We felt like if we were to solve this problem, we should do it in a generic enough way that it would be generally useful to the Go community. A lot of times I tell my engineers that we stand on the shoulders of giants. There are people who have already solved a lot of these problems, and our job is to learn from them and then decide how much of that we should be using, and if we should be introducing new things of our own. So we've done that for example, distributed transactions in Dgraph. We picked up from multiple different papers, from Spanner, from HBase, from Bigtable transactions, and so on and so forth. And then we ended up devising something which is a mixed strategy of all of these. And in caching, it was no different. We came upon Caffeine, which is extremely efficient, fast concurrent cache in Java, and it's being used by multiple databases in Java, including I think Cassandra, Neo4j, and any big Java system. we reached out to the author of that cache, Ben Mains, and Ben has been extremely helpful in helping us understand his implementations. He's written multiple papers about it, and also like to help us write our version of Caffeine, which is what we're calling Ristretto. Now, we did not pick up everything from Caffeine because Caffeine has been around for a while, and they are more sophisticated, I would say, than Ristretto is. But we came up with the initial good set for Ristretto, and I think some of the benchmarks that Caffeine had already done around concurrency, around hit ratios, etc., we learned from that. Now, we wrote a blog post about this before we started talking to Ben about the state of caching in Go, and for that, we just showcased all the different caches that are available in the Go ecosystem and just compared them. And we wrote some benchmarks for that, which were around throughput of the cache, etc. So we sort of like improved those benchmarks. We picked up more benchmarks from Ben, wrote them in Go, and that became our guiding sort of like light. So I would say Ristretto is designed in a way where it is generally useful for the entire Go ecosystem. And that's when Karl sort of came into the picture. He was recommended by Ben, and he came in and just started executing.
This episode is brought to you by TeamCity. TeamCity is a continuous integration and delivery server developed by JetBrains that helps software teams release their software faster, get fast feedback on every commit, quickly investigate build failures, and so much more. In this segment, I asked build engineer Oleg Garovich from Wargaming, who's been using TeamCity for 7 years, about what he loves about TeamCity.
So I love how easy it is to manage TeamCity on a daily basis. I don't have to hack any mysterious XML to configure it or make changes, though there is an ability to do that. I choose not to. I do most of my work through the UI. I also like the fact that I can customize a lot of its behavior, either through the UI or through custom programs that I wrote or through plugins with their open API. I don't think I could do my job without the support that TeamCity development team provides. And I use that support at least weekly, whether it's for new features that I'm interested in or for bugs that we find. They're very collaborative, and honestly, over the past 10 years, they've made my job so much easier. I really owe them.
All right, to get started with TeamCity, head to teamcity.com/GoTime to learn more. The professional version of TeamCity is free, even for commercial use. For large orgs, you'll want to check out the TeamCity Enterprise Edition. And right now, there's a 50% discount for our listeners on TeamCity Enterprise. And as a bonus, if you want a personal intro to our friends at TeamCity, they'll help you through your CI/CD path. Email me, adam@changelog.com. Head to teamcity.com/GoTime to learn more and give it a try.
So, Karl, how exactly did you start executing? What were you working on?
Well, actually, Ben found me on GitHub, and one of the papers that Ben co-authored with a few other people was called Tiny LFU. So we're talking about like the cache metadata as far as determining item value, like what you should evict, what you should let in. Tiny LFU is it was published late 2015, and it's called an admission policy, which I haven't really seen much of as far as in the literature. And so we all have heard the LRU eviction policies, and then the Tiny LFU paper was basically a new way of deciding what you let into the cache with a small memory footprint, and the eviction policy, it wouldn't even matter. It would just increase the hit ratio. So I was writing my own implementation. Of course, Ben was sort of looking around on GitHub, and I got linked up with Dgraph. And since then, we've kept the Tiny LFU
admission policy, and we're actually using the same counters for admission and eviction. So rather than doing like just standard LRU eviction, we're doing the sampled LFU eviction, which we've seen like some work done in Redis along those lines, and I think it's performing pretty well so far.
Talk a little bit more about sort of the admission decision, the policy. That sounds, I must admit, that sounds very unusual from what I'm used to in caching systems. Like, is it based on what? Like loosely, what is it based on? Is it like the frequency or the likelihood that something's going to be asked for? Like, what is that?
Yeah, it's based on the access counters. So you can think of it, each item, when you try to set a new item, it could either be accepted or rejected. So the TinyLFU admission policy will reject the items that it doesn't deem valuable. And to do that, we keep access counters for probably, I guess you would call it like a ghost cache. So like sort of some metadata for items that aren't necessarily in the cache. So if we see an item that gets someone tries to add it multiple times, and we see that it's valuable enough, eventually we'll let it in. And the idea is that the eviction policy would be like, it doesn't exactly matter as long as the eviction policy is good enough. The TinyLFU admission will give us a 10% hit or a 10% boost on the hit ratio.
To make sure I understand this right, that would generally mean that if you have some sort of new data that was just introduced in some way, that likely the admission policy is going to reject it the first couple times. So you won't see any performance gains up until, but at some point if people keep trying to hit that, so I guess a good example would be like if you had a new top story on Hacker News and everybody's trying to hit it the first few times, it might not be, but at some point it's going to end up getting cached. And then, because it's kind of learning, oh, this is important, this is something I need to cache, that's how it would work. Yeah.
And the TinyLFU paper, they also have this, it's a freshness mechanism. So if you think of an item that, well, if you just think of like the long tail distributions, the really popular items, like new items wouldn't really be able to compete with them. So the freshness mechanism essentially halves all the access counters for each period, which is, it doesn't really matter. But so we have the counters, and eventually new items do get the chance to go in. And yeah, I mean, it's about 12 bits of overhead for the amount of counters we have and for each counter. And Ben Mains has done a lot of documentation and research on it, and I think the benefits are pretty interesting because, like you said, the admission policy isn't really anything that I've seen, and I think for a modern cache, it's pretty much a no-brainer.
I find the concept pretty interesting because, like, we see it with Reddit, with Hacker News, like with websites like that, they're essentially doing the same thing, but it's more of like at a visual level, like for people, like to make it sure it's something that they actually care about. But I guess it's unique to see that applied somewhere else, like in caching, where you might not see it, but realistically, it does sound like something that would make a lot of sense because what the data people care about today is not necessarily the data they'll care about in 2 weeks, especially for some websites. As far as like that stuff goes, do you allow users who are using, like if I'm using a caching library, is that the type of thing that I could customize, like that refresh period, that sort of thing? Or is this something it's kind of like you fine tune it once and just work with it?
We obviously have like a configuration for Strato, so you can configure the number of counters, which since we keep metadata for items that aren't in the cache, so you could have so much ghost counters, I guess, that it might increase your hit ratio. I guess you can sort of fine tune it. Right now we found that the amount of items you expect to be in the cache, if you multiply that by 10, so 12 bits for each item, you find pretty good boost on the hit ratio.
Okay.
But I think just to answer that question, yes, I think we do allow a bunch of different options in how you can configure your cache. In fact, including we have this concept of lossy buffers. Because again, I think the big thing about Strato is that it scales really well, which means that if you're doing a lot of concurrent accesses, the cache should not slow down your system, which is the biggest issue we were seeing with Dgraph, is that when there were a lot of concurrent accesses, and Dgraph is a highly concurrent system, and graph queries can return millions of results in the intermediate steps. So you're trying to access millions of keys concurrently. Your cache, the locking on the cache becomes a bottleneck. And one of the big things that you wanted to avoid with Distrato was to even in the case of high contention and high concurrency, the cache should deteriorate in terms of hit ratios, but not in terms of the speed of the cache. And so we allow options of how many things that you need to batch up before they get applied. So, for example, the gets when you're doing tracking of the excess counters for the gets in the cache, you need to, for every get, you need to update a counter. Now, if you were to do it in the simplest possible way, you would acquire a lock, you would update the counter, you would release the lock. Obviously, that's not going to scale if you have a lot of concurrent gets. So one thing that Karl did there, which was really interesting, was that he used sync.pool to build up sort of like a stripe system for a buffer of gets. And one of the options is that is present in Distrato is that you can buffer up 64 gets before the stripe gets applied internally by acquiring a lock. And I think the throughput of that, Karl, was pretty high compared to some other things, right?
Yeah, I mean, I saw, compared to just like a naive channel implementation, the sync pool was probably 5 or 10 times the throughput, just because of the well, we have a pretty unique use case, but the sync pool internally it uses thread local storage. So, and per processor, so we don't really have access to that outside of the standard library. So the sync pool for our use case, which is basically we get a buffer, we get a stripe of the gets, and then eventually we drain it. So draining is essentially acquiring the lock and incrementing the counters. The sync pool works very well for that.
And actually, there were some GitHub issues that we pointed to in our blog post, where people are asking for that thread local storage, and of course they can't have it. So hey, the next best thing is to use what Go people have written, which is sync.pool. So Distrato actually is an interesting collection of a bunch of these. Do I want to say hacks? They're not really hacks, but they are just like interesting ways to use to get around some of the limitations of the Go language to increase performance, I would say.
When you have to do these things, like when performance is absolutely necessary and you're trying to make all of this work as well as possible, one of the things I think, I mean, you guys aren't on the show, but like Johnny and I talk about a lot is like making your code readable and easy to maintain. Would you guys say that your code suffers from that a little bit as a result?
No. And I can say that very confidently because I am actually I hate technical debt. In fact, the way we run things in Dgraph and all of our projects is that we consider user feedback to be the top priority, then comes bugs, then comes refactoring, and then comes features. So if we have a choice between refactoring a code versus adding a new feature, we will go refactor the code first. And if your code is clean, features they just fit in. They just fit in like a block. And so we spend a lot of effort on doing code reviews. I personally do a lot of code reviews for the growing team of Dgraph. And we always try to find the simplest possible way. So even these interesting, nifty things that we've done in Distrato, if you look at the code is extremely simple to understand. And in fact, I think that other engineers could potentially pick up some of these techniques in their own code and learn from our sort of little design things and implement it in their own code bases.
You've talked about like some of the things you've learned, like reading the Tiny LFU papers and talking with Ben. You've learned some stuff. I suspect you've also learned things on the other end of the spectrum, like things that you shouldn't do, or you probably tried some things and then realized that that didn't work the way we expected. Do any stories or experiences stick out in your memory? Anything that you'd like to share?
I think one thing that you mentioned was Hacker News before, right? And you said the new entry comes in Hacker News. You obviously want it to be serviced quickly. Now, I think if you were to look at the distribution of keys in that case, or distribution of accesses in that case, you would realize that the top 10 or the front page of Hacker News has exponentially more clicks than the second page of Hacker News, the third page of Hacker News. And one of the big things that we learned while even before we started building Ristretto is that there is a zip-f distribution, a Zipfian distribution of keys, which means that the most frequent keys are accessed exponentially more than the less frequent keys. And therein lies most of the downsides of current caches, is that they would end up hitting, even if you were to shard your data, let's say, right? You shard it, you put like 22, like let's say 32 shards, and you have a logo around it, you will end up hitting the same shard over and over again, because the few keys which are being accessed exponentially more times would actually end up on that shard. Right. So some of the typical strategies of, hey, okay, we have a LRU cache, why don't we just split it up into 32 LRU caches and we're going to use that. You end up going to the same shard, which means you end up having the same contention. And so one of the things that we wanted to avoid was for Zipfian distribution of keys, we are able to spread that around nicely. Right. So some of the things that we did with sync.pool, even if you are hitting the same key over and over again, you don't end up in the same shard or the same buffer on sync.pool, because sync.pool is going to give you something randomly, right? It's going to just pick up from one of the items that it has, it's going to give it back. And so we avoid that contention at that level. So these are some of the things that we learned. And the other things that we learned was, again, going back to the Go runtime is such a beautiful, marvelous thing, right? We wanted a fast way to get a hash. So instead of using, I think we were using Farm Fingerprint, which is a great hash by Damian Grisky, and we're using it in many places in Dgraph. We realized that if we were to like hook into the mem hash that Go uses internally, things are a lot faster. And once we had that hash, we are now using it for many different things by just doing a modulo of that. So there's just like these nifty things that we sort of applied to solve these common problems.
Given a scenario where you are lucky enough to know ahead of time that you're about to get a massive spike in traffic, right, and you'd like to absorb that as gracefully as possible. Is it fair to want to be able to pre-populate your cache and actually get the benefits that we've been talking about using Ristretto?
You could, if you knew, yes, you would absolutely go ahead and do the sets up front, so that you will just get the accesses. But I might argue that you probably would get them pretty quickly because, again, of the Zipfian distribution of the keys. So I think, when the first time, let's say, Ristretto sees a key, its counter is 0, right? It has never seen this key before. It doesn't know about this. So the chances of this getting admitted would be 0, right? But if it comes a million times over, pretty soon it's going to exceed anything else that the cache has. And that would happen pretty quickly. So there's it would come into the cache quick enough that I think that you wouldn't have to do anything specific at your end. It should happen naturally as the system sees this load.
That's pretty cool.
It's pretty cool, especially because I've seen, even at companies like Google, I've seen some weird practices around, like when a website's about to get a massive surge of traffic, engineers will do some weird things at times. The one example I can remember is Google Code Jam. I helped 1 year sort of organize things and run it a little bit. And right before it was about to go live with one of the competitions, they actually ran a little script that just basically hit this. I'm pretty sure it was just hitting the server to sort of get it ready for that influx of requests. And I think that was just a quick hacky, this will get it ready. It's fine. We don't have to do anything else. But I could definitely see that not being scalable all the time. In that one specific case where it's once a year or something, it's not too bad. But the other ones, it'd be much, much trickier. So it's nice to have options available.
And talking about predicting future, right? I think one of the good ways of figuring out how well a cache is doing is we talk about hit ratios, right? So Ben had written this particular future predicting system, which is which cannot be built practically, but for tests it's a great thing. And Karl actually replicated that and called it clairvoyant. Karl, you might want to talk about that.
Yeah, so I think there's a Wikipedia article on it, but it's called Bilaty's theoretical optimum. So basically the idea is you would play a trace over this implementation, and then you would run it back and figure out, use the future knowledge. You can use the future knowledge to essentially calculate the absolute optimal eviction candidates. So we don't have the luxury of that information in the real world, but with the Bilaty's algorithm, you can, when you run it back, you essentially figure out the optimal hit ratio. So when we're graphing all of these different cache implementations and Ristretto's hit ratio performance, we can use that ideal hit ratio to see how we're doing and how close we are to the optimal. Yeah, and it's been really useful. Ben pointed us to that, and caffeine has been really close to it, and we're trying to catch up.
So one of the features that I happen to really like with systems like Redis is that the automatic expiry of data, right? That is not frequently accessed. It sounds like you've got something a bit different going on here because of the emission policy and the ways you're choosing to sort of eject data out of the system. Can you talk a little bit about that? How do you handle, whether you even handle expiry at all?
Yeah. So I think at a very high level, right? What you want to do is you want to evict, if you're running at capacity, you want to evict something which has lower value than what is coming in, right? Because you're always trying to optimize the value of your cache. Now, what is value? That could mean different things to different people. And for Ristretto, the value means the chances that we will see this key come again, right? And in LRU cache, you say that, the one which was the least recently used, we would not see it again. In the LFU, which is the least frequently used cache, we say that, if this wasn't seen as frequently, we have less chance of seeing it. So we set the value to be the estimate of the counter, right? And the tiny LFU counter, the biggest thing a tiny LFU counter gives you is an ability to store millions of keys with very little RAM usage. So I think it uses, like, if I'm not wrong, 4 bits per counter, right? And so if you let's say think about 200 million keys, you can store their counters in 100 megabyte RAM, which is quite a lot. So the more you know about the universal set of keys, the better you can estimate their value, right? So cache running at capacity, everything that comes in should have a higher value than everything which gets out. So the juggling thing that Ristretto is doing is that for every incoming, we figure out what the estimate is. If we are at capacity, we try to create a sample set of what could be evicted and try to find the one with the minimum value. And if the entry has a higher value than the one with the minimum value, will admit the incoming and evict the one. Otherwise, if this one has a lower value than the one which is going to get evicted, we will reject the incoming. And I think that's the novel concept that is not present in typical caches, including LRU. That because in LRU, at the moment something comes in, it's admitted because it's the most recently accessed, and then it would evict something out. But to actually get better hit ratios, you really want to be judicious about who you let in.
This episode is brought to you by KubeCon, Cloud Native Con, and you are invited to attend this flagship conference from the Cloud Native Computing Foundation, KubeCon, Cloud Native Con North America 2019. That is a mouthful and an awesome conference to attend. It's happening November 18th to the 21st in San Diego, California. This conference gathers adopters and technologists from leading open source and cloud native communities. Use the code KCNA Changelog19 Once again, KCNA changelog 19 to get 10% off registration, or check the show notes for a special link to register and also a link to the Convince Your Boss letter. Again, check the show notes for links to learn more and register. And by Linode, our cloud server of choice. It's so easy to get started with Linode. Servers start at just $5 a month for your big ideas. Head to linode.com/changelog. Choose your flavor of Linux that works for you, then pick a location that's right for you. London, Tokyo, Dallas, and many other places in the world, they've got you covered. Go from having that amazing shower idea to a hosted website in just minutes. Start small, expand as your idea blossoms into a huge hit. And we trust Linode because they keep it fast, they keep it simple. Check them out at linode.com/changelog.
If I'm understanding this correctly, when you say you get a sample, is that you're not looking at all the data, you're just getting like a small subset of it and looking at that. So I assume that what that essentially means is even if you don't admit something right then, if it keeps getting hit a couple more times, because if it is actually popular, that's going to happen. At some point, that sample will actually show you something where it can get let in. So while it might not be the absolute optimal performance, it's going to be pretty good, especially considering that checking everything in your cache is not feasible at all. That would take up way too much time. So the idea here is to kind of play these statistical, we're trying to be as 90% or something like that without wasting a lot of time getting it. Is that correct?
That is correct. And I think so. There's two different things happening here, right? One is the incoming. One thing that we do is that irrespective of whether we admit a key which is incoming or not, whether we reject it or admit it, we would always update its counter, right? So we can keep track of how often we have seen this thing, so that it would keep on building its value within our system. And so at some point, once the value of this key is higher than the eviction candidate, it can be emitted, right? So everything just keeps on building value. The second thing is that, and that comes back to the idea of, hey, how complex is our code? Now, one way to figure out the eviction candidate is to keep track of all the values of every key and do maybe a priority key or something, and find the key with the minimum, right? Obviously, more code might be slower, might have issues because the values are constantly changing. So all we did was we said, Go Maps gives you a pseudo-random access to the keys. We already know that, right? It's not completely random. If you go, people have done some tests, and it shows that it prefers certain keys over others, but it is still random in some level. So we were like, hey, why don't we pick, let's say, 5 of these keys that are coming to us at random, and use that to find the candidate which would have the eviction candidate with the minimum value. And so if you can imagine, the code is really simple to find 5 things from a map, right? We just loop over it 5 times. But that gives us a pretty good hit ratio, as Karl's benchmarks showed. So we were within 1% of what would be a priority queue approach to finding the eviction candidate.
So yeah, I find that's that aspect of it really interesting, because if you're studying algorithms or any of that stuff, you learn about things like the traveling salesman problem, and these things that realistically solving them perfectly are not possible. It takes way too much time and it's way too hard to do. But as engineers, we've kind of realized that if you can get within 10% of the best solution, usually the difference is so minimal that it just does not matter. Yeah. And it sounds like you guys are taking the same type of approach where, for caching, it might not be optimal, but optimal is going to take so much time to verify and to make sure it's always there, that being optimal is not actually faster because of all that extra work. So it sounds like that's a really unique approach, and it sounds like it's working really well, which is cool.
Right, and I think that's the one thing that we keep on doing is we like to go for good design, but at the same time we also like to be judicious about is this extra design worth the extra code complexity. So the juggling act of maintaining simplicity of the code with the performance of the design, that's very crucial for us at Dgraph, and that you will see it across all the different things, including Dgraph the database, Badger, and as well as Ristrato.
today, Ristretto is a library. It's something that you didn't import and use into your code. But in my mind's eye, I could definitely see a server implementation of this, even with the network hop. I think it would still be efficient in given certain circumstances. Is there plan around having sort of a server model for this?
We have been asked about this. If it's useful to Go community or in general to the wider dev community, we would be open to writing something like that. It should be relatively straightforward because all you have to do is put a network thing on top of it. But then I wonder, hey, we already have Redis, we already have memcached. People are pretty happy with that. Is it worth it? We just don't know. We could be convinced.
You might be underestimating developers' desire for novelty.
Yeah, if there's enough demand for it, we would love to build something.
So when we talk about this type of caching, where we're getting into slightly more complicated, I know that you had mentioned that from the developer's perspective, it should be, you kind of like it to be almost like they don't know a lot of the details, so they don't have to worry about them. Is that true?
That's the idea. I think we keep the options to just like what they really can understand and nothing more. Yeah.
So that would mean that realistically, there's no harm in using this over, say, some other least recently used cache or some other naive approach that they could implement themselves. But I mean, if that's what they want to do, I guess the implementing it themselves has some merit. But if they're going to pull in a library at that point, it doesn't really make a difference which library they pull in because they all should realistically be making it easy. So it's just a matter of the most performant one.
Absolutely. And I feel like the problems that we ran into are general enough problems that other developers could learn from or could benefit from. And again, we are not the only ones because caffeine already exists. There's multiple papers about caffeine. It's already being used. And so I think one of the things about when we were starting this project was, we are a small company with limited engineering resources, and like what we should be prioritizing is extremely, it's a highly debated thing, right? But one thing that kept us going about building this cache is that we felt like, Java has a lot of interesting things that Go does not have. For example, a lockless map, which runs at atomic level. Now, the kind of throughput that you can get from a Java's lockless map implementation is, I don't think it can be matched in Go. But at the same time, we all love Go. Go is an amazing language. It is so simple. It is so easy to use. The code is so readable. It's, what else would you use? You won't use Java. And so part of our effort was, let's bring the Go ecosystem closer to Java's. And I always joke in the company that, Go is like the Wild West. It has a lot of opportunities. At the same time, if you want something, you have to go build it. Right. And so this was an attempt by us to get the Go ecosystem to be at the same level as where Java is.
So would you say today that if I'm sort of your average Go developer and I'm building an application or service or something that could benefit from cache, that I should definitely basically consider Ristretto, where I would typically rely on other libraries that are perhaps that have been used for a while. So there's no what's the requirement, or rather, how should I be thinking about when to use Ristretto?
Use it if you have one Go routine. Use it if you have 20 Go routines or 100 Go routines. I think Ristretto is ready to be used, I would say. Right. I think we have some bugs in the system that we already know about, that we're already working upon. But I think the idea for Ristretto was to unite the Go community around a cache which is designed for scalability, designed for performance, designed for better hit ratios, all the things that a cache should aim for. Ristretto is going for that. And over time, I have no doubt that Ristretto would become the default choice for Go ecosystem.
Like, more generally speaking, I don't think a cache is always the best choice for, like, let's say I'm throwing together a web application. Realistically, there's some point where you need to start thinking about caching. And I think you even said that for you guys, you weren't using a cache necessarily the whole time, or like you had one and it was slowing you down more than it was helping you. So if you were talking to somebody who's sort of starting up something new and trying to pick and choose where to spend their time, around when do you recommend they start looking into caching options and that sort of stuff?
I think ideally the system has been built in a way with a good design that the latency of the requests to the system are fast enough that you do not need a cache for a while, right? So Dgraph currently does not have a cache, and we released version 1.0, we are at version 1.1, and so on and so forth. We still don't have a cache, and it's performing really well. Actually, it's outperforming a lot of other databases. So ideally, you build a system in a way where you can go without a cache for a while, because introduction of caching is a hard problem. You introduce correctness issues, you introduce contention issues, you introduce 20 other things that you don't even know about, right? But it's more like a double-edged sword, right? It can really get you going really fast. It can really improve the latency that you have. At the same time, you could end up returning the wrong results, right? So in general, I say just be careful around using cache. But once you know that caching can really improve your latency, go ahead and use it, but do a lot of correctness testing. And as I mentioned earlier in this talk, in a multiple version concurrency control system, caching becomes particularly hard because each version has a different state for the same key. Then you need to be even more careful. So one of the things that we're going to do with Dgraph is, as we introduce Restrator to Dgraph, we're going to be running Jepsen tests on it to make sure that we haven't introduced any new correctness issues to the database. However, some of the initial benchmarks that we are doing do show a very positive impact on the latency numbers. Like the latency actually is improving because of the cache.
So when you talk about running a test this way, it's not like your standard unit test where you can just test one thing in isolation, I assume. I assume this is something where you have to orchestrate a whole lot of things working at the same time. I guess we have a tiny bit of time left if you guys have a couple more minutes. Yeah. Can you talk a little bit about like how you went about that testing and how you made it reproducible, how you made it useful? Because I know from my experience, the more pieces you get involved in a system, like in a system test, the harder it is to reproduce it, to actually figure out what went wrong. And like they become way less useful in some ways because it's just hard to actually figure out what broke. So have you guys learned anything from that process, or is that anything new coming from that, I guess?
So we have multiple levels of tests. We have tests within Restrator for Restrato's own correctness. And then we have tests within Dgraph written by us, which are around Dgraph's correctness. And then we have Jepsen test, which is the third-party distributed systems test for the database, which kind of like test correctness while introducing a whole bunch of edge case scenarios like network partitions and machines getting lost and processes crashing and so on and so forth. I think you need all of those really. You need to test for correctness as multiple different levels. And the thing about correctness testing is that a lot of times you don't know what you're looking for. You're just throwing things at it, expecting them to run. For example, Badger has a bank test, and we run it for 8 hours every night to like move money around between accounts and make sure that the total amount in the bank has not changed, right? So some of these things you can do it directly on the component itself, but I think there's a lot of value in having a higher level test which does not care about any particular component, but just lets you know if something is broken in terms of correctness.
So this is kind of like, I think it was a couple weeks ago, Matt talked about security, and in there they talked about fuzzing and sort of just sending random data. So the idea is to come up with something that you can be verified. Like you mentioned, if you have a bank, there's a total balance that should realistically stay the same. And then from there, it's a matter of just throwing whatever you can at it. So there are ways to sort of, like you can verify that things are working, but at the same time, it's random enough that you can test things that you don't even know what you're testing for, which makes that unique in that sense.
Exactly. And some of these tests, they would not tell you which part is broken. And that's not the job of these tests. The job of this test is to tell you if the entire system has an issue or not. Just that and nothing more. And then you have individual tests which will tell you, okay, this particular part is not working correctly. And then we go to like distributed tracing and all that stuff, which can help you identify these issues. But I think you do testing at multiple different levels, and I find a lot of value in these black box testing, I would say, where the system should act in a certain way, and that's it.
Yeah. See, I completely agree with you. I think it's also hard when you're on the other end of it where it's broken and you don't know why it's broken. So you just want to bang your head off a wall for a while. So it's not that I don't see value in the, like I see value in those tests. It's more of a, trying to figure out how do you actually take the fact that a test is wrong and turn it into something to act upon and fix. That sometimes becomes a challenge. I
would give you a story about exactly that scenario. I think my last years was spent on trying to fix some of these Jepsen tests. And Jepsen is this black box testing scenario where it was just tell you that the system has a problem, but does not help you in any way in identifying what the problem is. And I think me and my engineers, we spent many months trying to figure out all of the issues there and why that issue was being caused. Ultimately, we introduced open census tracing into Dgraph, and by connecting that to Jepsen's own tests, we could track it all the way down to the last part, and that helped us get an insight into what might be going on. And we had to write these crazy scripts to figure out what was the state of the system at that time. So we had to do a lot of things to be able to understand why the test was failing. It took us a while, but if that test was not even there, we would think that it's working just fine, right? So yeah, I think some of these, I'm a big fan of open census. I think having that and open tracing, etc., all those things are just incredible. So one way to deal with some of these issues is to add more instrumentation.
All right, well, I think that about wraps up this episode of Go Time. Thank you, Manish. Thank you, Karl. And thank you, Johnny, for joining us. If you have any other questions, you guys can definitely ask in the Go Time Slack. If Manish and Karl, if you guys want to check out that Slack channel and answer some questions, I'm assuming you guys can. But yeah, that sums it all up.
We will. Thanks, guys, for having us.
Thank you.
All right, thank you for tuning into this week's episode of Go Time. If you're not yet, hang with us and go for Slack. We have a channel called Go Time FM. Look it up, you'll find us. Hang with us during the live shows, connect with other members of the community, share stories, share code, share coffee recipes, whatever. It's a lot of fun. Also, we have discussions at changelog.com on every episode. Head to changelog.com/GoTime, find this episode, and discuss it with the community. Also, thanks to Fastly, our bandwidth partner, Rollbar for helping us move fast and fix things, and Linode for hosting the Changelog platform. Our music is produced by the mysterious Breakmaster Cylinder. And if you want to hear more awesome podcasts like this, subscribe to our master feed. It's one feed to rule them all, plus some extras that only hit the master feed. Head to changelog.com/master or search for Changelog Master in your podcast client. You'll find us. Thanks for tuning in. We'll see you next week.